on the beta ansatz for this model. The time limitations mean that I won't be able to talk to you about more advanced things like the algebraic beta ansatz version of this model, but we'll see how we do anyway. So I really welcome questions during the presentations. It's very boring for a teacher to just talk and talk and talk and talk and have no questions, because then you think you're kind of either shooting way too high or way too low. So please interrupt me if you have any interrogations about it. I've just given a set of printed out notes to Andrea. I guess you'll receive that at some point, since I'm very afraid of Edward Snowden and Vladimir Putin and that sort of thing. You'll get some printed copies of them. Okay, very good. Now, as you can see, I'll just use this kind of electronic blackboard. So these things I'll put on PDF on the website once we're done. Okay, so let's just do this. So let's just get started a little bit. Essentially, what I want to talk. Let me just change something. What I want to talk about is a very let me start. Where's my system references? Right. So we're going to talk about the one-dimensional Caux gas. 1D Caux gas. Okay, one thing I have to warn you about is that my handwriting is absolutely atrocious. This is not something I can cure. There is no known cure for this. This is part of the reason why I give you printed out notes as well. So many of the things I will write down here will be utterly illegible, but view this as a bit of a challenge to test your understanding of what I'm talking about. Now, before we talk about the 1D Caux gas, and specifically the Liebig model, maybe there are just some things to be said about interacting particles in one dimension. So you might be interested in looking at generic Hamiltonian for particles in 1D. So typically what we'd like to write is maybe a kind of theory where you start with a Hamiltonian that's composed of two different pieces. First of all, there's going to be a kinetic energy piece that you would just write, for example, as an integral over a spatial interval, which we leave unspecified here. It's probably the whole line as a first consideration. And then you want a kinetic energy term, so you'd have your creation operators, and then you would put some kinetic energy in there, so h pi squared over 2m, with some second derivative here with respect to the coordinate, and then you'd have your annihilation operator psi of x. So just some free kinetic energy, k squared over 2m. But then you would like to complement this with, most interestingly, some interactions of density type. So you would just write maybe some potential that could be spatially varying, so you would have an integral dx1, dx2. You would have some potential, which in a translationally invariant system would depend on the difference between the coordinates. And then you would just have the normal ordered density interaction. So x2. You're falling off. Ooh, okay. Well then I'll show you a trick. That's a nice trick here. Wow. Okay. I'll try to make sure I don't go over this line here. So times just the psi of x2, psi of x1. Okay, it's falling off like this. Try to sort this out at the break. Okay, so now the first remark that you can make, of course, is that if you have particles of given statistics in 1D, the effect of interactions is radically different. If you have fermions, of course, things are relatively simple. If you have spinless fermions, then if you focus on, for example, interactions that are typically contact interactions, so these would be non-zero only if the coordinates coincide, then fermions would remain totally unaffected because of the antisymmetry of the wave function. So in the case of fermions with a contact interaction, the ground state is of course a Fermi C. Okay, so if you have just fermions, So if V is like delta of x1 minus x2, this has no effect. The ground state is just some Fermi C. Okay, and then, so you remember how that goes, right? So the Fermi C has a width of 2kF. 2kF, you have to fill in all the fermions in there. So you put one fermion per momentum mode, 2 pi over L. So essentially that gives you a ground state energy which is proportional to kF cubed, right? Because the energy of a single particle is k squared. You integrate that up to kF, so it's kF cubed. So the ground state energy is proportional to density cubed for fermions. Okay, so this is just elementary. Of course, if you have bosons, first message is that in the case of spinless fermions, contact interactions are utterly unimportant. They don't affect anything. Fermions are insensitive to contact interactions. You need longer range interactions in order to achieve anything. In the case of bosons, however, of course, it's completely different, because bosons, without interactions, they collapse onto a BEC-like state where all bosons fall into the zero momentum mode, and they occupy that. So when you turn on interactions, contact interactions in the case of bosons, the effects are quite radical. Okay? Bosons without interactions don't have anything like a Fermi C. It's just a delta function at k is equal to 0 for the occupation. But when you turn on interactions, this has drastic effects, because of course suddenly the bosons cannot, they push against each other. So the effect of perturbations in the case of bosons with contact interactions is very radical. Okay, so as a first discussion, we'll just try to understand the effects of interactions a little bit better as we go along. Okay, so what we will focus on is this case here. Okay, so we will focus on the Lieb-Liniger model. You will get used to my handwriting, don't worry. Everybody gets used to it. So, in first quantized notation, what we're going to do is simplify our lives. We're going to put h bar is equal to 1, 2m is equal to 1. So our Hamiltonian is just going to be a summation over n particles with just the kinetic energy part, so dxj squared. And then our interaction is going to be a contact interaction. By convention, we will give it the parameter 2c here. It's a pairwise potential, so there's a summation j1 less than j2 of the delta of xj1 minus xj2. Okay, just before I fall off the edge of the cliff. So, of course, this has an equivalent second quantized formulation. You can also write it in the following way, as a field theory, just integral dx. You can use a symmetric part here, dx psi dagger, dx psi plus c psi dagger of x, psi dagger of x, psi of x prime x. Okay, so this theory here, if you write its equation of motion, as is well known, so you get I dt psi is equal to just the commutator of this h with the psi. And this is just the well-known nonlinear Schrödinger equation. Okay. Okay, so this is, well, there's a psi here that fell off the edge of the world. So it's just a nonlinear Schrödinger equation. Okay, and you'll find that in many books. Actually, in terms of references, of course, you can find many of the things that I will talk about in a couple of books. Most famously, of course, the kind of purple brick from 1993, Koryepin-Bogolyubov-Zergin, about quantum inverse scattering method and correlation functions. So they have a very good presentation of the 1D Bose gas in there. There are also other books, Takahashi's book about thermodynamics. This one goes much more succinctly on the Bose gas and things like that, but you can still find a lot of things. And there are other books also, so Sullivan et al., but you can just find many things in there. Okay, so we've specialized in the case of contact interactions, and immediately we can say a number of things about this model. So there are two conserved charges in there, which are trivial to formulate. So trivial charges. You have just the total number of particles, which is integral dx psi dagger psi. And you have the momentum operator, which you can also just write as a symmetrized form minus R2 integral dx psi dagger dx psi minus dx psi dagger psi. Okay, so you can verify that these two objects commute with the Hamiltonians in the second quantized formulation. Therefore, eigenstates of the theory will be will have a well-defined number of particles and a well-defined momentum. Okay? So the problem that we would like to solve is just the Schrödinger equation for either the first quantized or the second quantized version of this. Now, these two formulations are completely equivalent, so you know, the first and second quantized version. So they're linked by just writing a state with n particles as the spatial integral, so the n-fold spatial integral of some amplitude psi n that I'll try to write as a capital psi that depends on these coordinates, and then just the operator, the gradation operator is at x1, xn. Am I falling off again? So this acting on some Fock vacuum 0. Okay, so you know the Fock vacuum is just annihilated by all the annihilation operators. And you can link the first and second quantized formulations of the theory by such expression here. So essentially what we want to solve is the time-dependent Schrödinger equation. So we have the Hamiltonian acting on psi n, and we want this to be diagonalized, En psi n. Okay, and this is equivalent to just doing it in first quantized notation. So here, by a kind of abusive notation, I use the same h, but here I'm in the first quantized version of it. And then you have this function here, psi n of the set of coordinates here is equal to En times this function. Okay, so that's what we're going to try to solve. Now, before I get going, I actually want to maybe present a tiny bit of physics. I'll try to do that very, very quickly because well, time is limited. Of course, if we don't think we can solve something exactly, then we look for smart approximations to the theory. Now, one smart approximation for interacting boson systems in any dimension is Bogolyubov theory. How many of you have seen Bogolyubov theory? Did you study that? 2, 3 of you. Okay, so then I can 4. Okay. So then maybe I can go very, very quickly through that. So let's just discuss Bogolyubov theory for the system. Okay, so let's just get some notations. So we will first of all introduce some Fourier transforms of our fields. So we're going to write the field operator psi of x as just 1 over L summation over some momentum indices e to the I k x times psi k. Okay, the inverse transform is quite simple. The canonical commutation relations in these conventions here are that in the Fourier space you have the commutator between k and k prime modes. This is equal to L times the Kronecker delta of k and k prime.
I'm falling off.
Fell off again. Okay. I tried to adjust it here, but that's not quite good. Okay, delta k, k prime. If you rewrite the Hamiltonian, so you know, for simplicity, we just use periodic boundary conditions here. The Hamiltonian you can just rewrite in terms of these modes as 1 over L summation over k of k squared with the occupation psi dagger k psi k, plus then the interaction term, c over here L cubed, and then there's a summation over k1, k2, and q, and then it's a flat summation, psi dagger k1 plus q, psi dagger k2 minus q, psi k2, psi k1. Okay? So you have an interaction term that redistributes pairs of momenta into shifted pairs of momenta with a q momentum transfer between the two particles with the same amplitude irrespective of the momentum transfer. Okay? This is a consequence of the ultra-locality of the interaction. The delta function is just essentially the summation, flat summation over all momentum waves, all e to the ikx. Therefore, you can transfer any momentum with the same ease. Okay, so now what you expect in the presence of weak interactions, so of course if you put c is equal to 0 in here, your ground state is going to be everybody sitting in the zero momentum mode. So if you have big N particles, essentially the operator psi dagger k psi k will count N particles in the zero momentum mode. So Bogoliubov theory is essentially a modification of that, where you treat the effective interactions starting from the knowledge that the zero momentum mode is macroscopically occupied. Okay? You do. It's a kind of approximation which works, or should work very well in the limit of small c. Okay, so what you do is you do you follow Bogoliubov's idea. You separate the number operator into a number operator for the zero momentum mode, plus then the summation over non-zero momenta of psi dagger k psi k. Okay? And what you expect is that the expectation value of n0 is of order of the total number of particles. Okay? So you have a quasi-collapse of all particles onto the lowest available state. Instead of having a Fermi sea, everybody goes into the same state. Okay, now there's a bit of algebra associated to it. I don't know if, it's kind of, well, the results are in the notes. Maybe I can just see how long it would take me to do this. You've ever done Bogoliubov transformations and things like that? Do you want me to do this? It would take like 10 minutes. Or are you... Yes? No, I don't do it, eh? Okay, very good. So, what Bogoliubov, okay, so the story goes as follows. For those who have not done it, it's relatively straightforward. What you do is that you look at your Hamiltonian here, especially the interaction term here. Okay? Now, in this interaction term, of course, there's this threefold summation over momenta, but you separate each of these summations here into two different pieces. First of all, the term where the momentum is zero, and second, the term where the momentum is non-zero. Okay, so there are many combinations here. There are 6 possible combinations of terms here. Well, there's one combination where all these k's are 0. Okay, then that gives you a term of order n0 squared. Then there are 6 combinations where 2 of these 4 operators have momentum index 0. So that gives you a term of order n0. Okay, which then comes to correct the dispersion relation here. Just imagine, for example, that this momentum is 0, this momentum is 0. Then you effectively replace this object here by some n0, which shifts this thing here. So there's going to be a correction here proportional to n0. Now, of course, it can be that these 2 indices are 0 and these 2 are non-zero. So then you get a BCS-like theory for your bosons. Okay? There's a propensity of the system to, of course, the eigenstates of this system, they don't conserve the number of particles in the zero momentum mode. It's like a BCS superconductor, but just bosonic. You have terms of the form psi dagger, and psi for the k non-equal to 0 terms. Okay, and that's what you can rediagonalize with Bogoliubov transformation, and then you can write the ground state energy and the whole spectrum of this. So let me just give you the answer. The result is that you can rewrite the theory in the following way. So the Hamiltonian gets simplified into some constant E0 that I'll just tell about a little bit more, plus modes that live at non-zero momentum, but that have a dispersion relation, which is the Bogoliubov dispersion relation that I'll write down in a very short while. Okay, so these are just transformed fields. So the epsilon Bogoliubov of K is essentially the free dynamics that we have, but corrected with a term which is proportional to the density of the system. Okay, so in these units here, this is k to the 4 plus k squared times 4cm, right? All to the power 1/2. Okay, so it's very striking, because if you have a finite density in your system and you go to very low momentum, this becomes linear in momentum. Of course, at very large momentum, this is just proportional to k squared. So at very large momentum, it doesn't matter whether you've got a background of particles in a quasi-DEC state, you still have free dynamics. But if you're at low momentum, what you see essentially is that you are greatly affected by the zero momentum states in there. So you see them. So the dispersion is linear in k at small k. Do you have a question?
No C dependence. I mean,
I'm sorry?
There is no C dependence.
This is a C, right? Interaction here.
Ah, okay.
Yeah. 4C, I'm sorry, I should have told you that. So N is the particle density, N over L.
Sorry.
Okay? Oh, well, sorry if it's not clear. Okay, so C is the interaction term. And you get this. Now, what you obtain as well is that the E0 you can calculate within this approximation. So this E0 takes the following form. Actually, if you just calculate the energy density, you get that it's C times N squared minus some constant 4 over 3 pi times C times density to the 3/2. Okay, so this is often written in the following way: N cubed gamma times 1 minus 4 over 3 pi square root gamma, where gamma is by definition C divided by density. Okay, it's a reduced interaction parameter. Okay, just a few words of comments on this. So first of all, of course, the ground state energy has a very different behavior than a fermionic energy here. What? How did it get erased? Thank you. So, of course, the ground state energy is very different to that of fermions. You just end up having ground state energy, which in fact is non-analytic in the interaction parameter. So for a fixed density, there's a correction of the form interaction to a fractional power, 3/2. That's very, if you want, disheartening if you're thinking of doing a perturbation theory around the C is equal to 0 point. Okay, so it's very often said that you can't do perturbation theory around the C is equal to 0 point for these interacting bosons. It's not technically correct. You can do perturbation theory because that's exactly what Bogoliubov theory is. It's just you have to be smart when you do it. You have to realize that one of the modes gets macroscopically occupied. Therefore, for this mode here, the effective interaction parameter is C times the number of particles. Okay? So it's very sensitive. But you can still do this. Okay? So what Bogoliubov theory tells you is that there's the development of a finite rigidity in the system. The C has a finite energy. There's a finite momentum spread now in the ground state. And essentially this dependence on the interaction is very atypical of the systems you have because you're used to fermionic systems because of this fractional power of the interaction parameter. Okay? Now, maybe just a couple of other comments. In which limits does Bogoliubov theory work? Well, just by looking at this, you can already fix some very trivial limits here. there is no way that the ground state energy can be a negative number, because the ground state energy is essentially just a kinetic part plus an interaction part, and the interaction part is made of an operator whose matrix elements are strictly positive, so it can only increase the energy. Therefore, your gamma is already limited by, 3 pi over 4 squared, which is, 5.55. Okay? But you can be one step smarter than this. You can use a theorem which is called the Hellman-Feynman theorem, which essentially relates so you take the ground state energy and you differentiate it with respect to the interaction parameter. And what this has to be equal to is the expectation value in the ground state of the operator in the Hamiltonian that's coupled to the interaction. So you just have expectation value of normal ordered density squared in the ground state, and this has to be a positive number. Therefore, the derivative of the ground state energy with respect to the interaction parameter has to be positive. And that gives you a stronger limit on the applicability of Bogoliubov theory to the Bose gas, because then it tells you that gamma cannot be higher than pi over 2 squared, which is like 2 point something. Okay, so Bogoliubov theory is a good approximation of weak interactions, but when interactions become of order 1, it will break down. Okay, so you have to go further. In higher dimensions, this is not the case, actually, so you can trust your Bogoliubov theory a bit further. Okay, but that's just a first part. So one of the things we will expect out of our exact solution is some fractional dependence on this interaction parameter. So we're not going to do perturbation theory, we'll have to do a little bit better than that. Okay, yes?
Apart from what you just said, what is different with respect to three-dimensional case? I mean, the superfluid theory standard.
So it's much more robust, if you want. So the
treatment is the same.
Absolutely. So the treatment, but you can literally do this in higher dimension. You will get, of course, a different dependence on density and the ground state energy, because then there's the Jacobian and the integration. But for the rest, it's completely identical. Okay, so there's also a limit to the applicability of Bogoliubov theory in higher dimensions, but yeah, it's a bit more. It's okay. Right here, it's lower. The difficulty here is that there's only one way, if you want, one set of modes in which the ground state can kind of radiate out. Higher dimensions, of course, this is very different, but then there's much less correlation between the, kx, ky, kz modes, so it's a bit more robust. But still, Bogoliubov theory in 1D, despite the fact that you don't develop a true BEC, it's still, a very, very good approximation. Much better than people actually say. Okay, so even if you do correlations and stuff like that, Bogoliubov theory is actually not that bad. Okay. Okay. Anyway, so that's Bogoliubov theory, and now before the whole day is out, let's get down to the real business. Okay. So what we will try to do now is construct explicit eigenstates for Lieb-Liniger. Okay, so we will now look for eigenstates. And what we will do is we will start with two particles. Okay, so we will do a baby problem at first, which turns out to point the solution for the general case relatively straightforwardly. So the Hamiltonian that we will consider is the two-particle form of Lieb-Liniger. We will just have minus d x1 squared minus d x2 squared plus then 2c times delta of x1 minus x2. Okay, now you've all solved essentially this problem in basic quantum mechanics. You have certainly all solved the problem of scattering from a delta function potential. And you will remember that the consequence of a delta potential is to introduce a cusp in the wave function. Okay, so the wave function itself remains continuous, it has to. The first derivative of the wave function, however, obtains a discontinuity. It will change by a value which is proportional to this c. Okay, so this is just a straightforward straightforward thing. Essentially, what you can do is you can, for example, move to relative coordinates. Call it x plus is the center of mass, so 1/2 x1 plus x2, and then x minus is just x1 minus x2, and then you integrate x minus in a small interval, call it minus epsilon to epsilon, okay? And this is going to give you the condition for the discontinuity of the wave function. So the equation that you obtain is that minus 1/2, if you rewrite it in terms, so let me just write this, d1 minus d2, where here I mean d versus dx1 or versus x2, with the twofold two-particle wave function here. This evaluated at x1 minus x2 is equal to minus some little thing. Okay, so let me write it like this, minus 0 plus x1 minus x2 is equal to 0 plus. Okay, this plus c times the wave function evaluated at x1 is equal to x2 has to be equal to 0. Okay, so I guess you've seen this before. Now this is the completely generic equation for a wave function whose symmetry properties are not specified. We are dealing with a bosonic wave function, and therefore this function has to be symmetric in its two coordinates. Therefore you can just slightly rewrite this as the following equation. So using symmetry, you just get that the condition is that the derivative with respect to x2 minus the derivative with respect to x1 minus the interaction parameter applied on the wave function evaluated at, let me actually rewrite it in this way, so x2 minus x1 is equal to a small positive number. This thing has to be 0. Okay, so this is the cusp condition. Okay, I mean it's, I'm sure you can do that very easily. Okay, so now essentially the strategy for the solution is as follows. We are looking for a wave function psi2 which is defined for all coordinates x1 and x2. Okay? So of course if x1 is different than x2, then the interaction term of the Hamiltonian is 0. Right? And therefore, for coordinates that differ from each other, the solution of the Schrödinger equation is just a product of two plane waves. Okay? Now, in order to solve the Schrödinger equation for all x1 and x2, what we can do is solve the Schrödinger equation in a domain where the particles have definite ordering. Say x1 is less than x2. In this whole domain, the solution is just a linear combination of the two possible plane waves that you can have. Okay, so maybe I can just write down. So we define a, so in domain D2, which is by definition x1 less than x2, okay, the Schrödinger equation is solved by a form e to the I k1 x1 plus I k2 x2, okay, or e to the I k2 x1 plus I k1 x2. Okay, so these are two degenerate wave functions. They have the same momentum, they have the same energy, which were our two conserved charges that we already have. Okay, so in this whole domain here, D2, a linear combination of these two solves the Schrödinger equation. Now when we when we want to solve, once again, the Schrödinger equation for all coordinates x1 and x2, what we can do is solve for the Schrödinger equation in this domain D2, complemented by the boundary conditions defined by the cusp condition written above. Okay? If we have that, then we have the wave function in the whole domain, because we can just extend this fundamental domain D2 by the symmetry of the bosonic wave function into the other domains. Okay, so these are just two equivalent ways of doing it. The easiest way is to do it this way. Okay, so now what we do is that we so here with this form here, the energy is of course going to be just k1 squared plus k2 squared, and the total momentum is going to be k1 plus k2. Okay, so we're now ready to put the form of our wave function into this equation here. So what we will do is we will do an Ansatz. Yes, that's the German here. We do an Ansatz, a guess for the two-particle wave function of this form. We will say that the two-particle wave function, dependent on coordinates x1, x2, and with, if you want, labels k1, k2, just quantum numbers, is going to be a linear combination of, well, let me actually even be more precise. We will say that in domain D2, so x1, x2 are in the domain D2. We will say that it's a linear combination between two parts. So there's going to be, first of all, e to the I k1x1 plus I k2x2. And we will give that some amplitude S1, but then there's going to be also the permuted the permuted wave numbers with the two particles. So these two things give us a chance of being able to solve the Schrödinger equation equivalently of solving the boundary conditions. Okay? So the boundary, it gives us the following condition. Yeah, so if I just go back here, you remember, so dx2 minus dx1 minus c on this thing has to be 0. So we just apply this condition here, and this immediately gives us a condition on the ratios. You see, if I take dx2 minus dx1, I just get ik2 minus ik1, then there's a minus c times s1, plus here just ik1 minus ik2 minus c times s2 is equal to 0. Okay, so then you just rewrite it. It just gives you a condition that S2 divided by S1 is equal to the following things. So minus C plus I K1 minus K2 divided by C minus I K1 minus K2. Okay? So the boundary condition has fixed the ratio between these two different linearly independent parts of the wave function, these two free waves that we have here. Okay? So the interaction essentially sets the way the momenta has to be distributed in amplitude, or if you want, the amplitudes of the different momentum permutations have to be related to each other. Okay? So this is the first form of a beta ansatz. It's a two-particle version of the beta ansatz. The beta ansatz is always of this form. You can view it as just a glorified Fourier transform. So you're used to the Fourier transform in everything that you have. Of course, the efficiency of the Fourier transform is that the different momentum waves don't talk to each other. It doesn't really matter if you have a many-bodied Fourier transform in there. You write it just as a product of Fourier transforms. Maybe with a kernel that's very complicated, but it doesn't matter. You know, you just do your Fourier transforms independently. In the case of the beta ansatz, what happens is that the domains of integration that you have for your free waves is limited. Okay? So for example, if you have two particles and I ask you to do a Fourier transform, what you will do is that you will take your function and you will integrate both x1 and x2 from minus infinity to infinity independently of each other. Okay? In the case of the beta ansatz, essentially your coordinates are restricted to these domains. If you want, it's like a Fourier transform over an interval that is dynamically set. Okay? But it's very much like a Fourier transform. So that's the general form. And the nice thing also about beta ansatz is that all the models that we know how to solve with beta ansatz, it's kind of a tautology, they have the same form of wave function. You always have this thing here, so you'll see that with the xxz case, xxx case. The wave function will look absolutely exactly the same, especially after I've written it in a kind of more compact fashion. Okay, so we'll just try to synthesize the notations a little bit. So, so just a notational. So since this is complex number divided, yes, question.
How can you say that these are all the solutions of the problem, initial problem?
So we have not classified the solutions yet. Okay? What we have here is essentially a token model, a template for the solutions. We have not specified the values of momenta, K1, K2. Okay? So what you would guess at first is that all wave functions of this model take this form here, and the catalog of wave functions is labeled by these momenta K1, K2. Okay, but we will talk later about the classification of eigenstates, and then we will see what restrictions there are on K1, K2. Actually, so that's a first good comment to make. So K1, K2, they're just completely free numbers. I'm even allowed to put, for example, complex numbers in there if I want, at least to try. So what happens if I put complex numbers K1, K2 in there? Well, there are some restrictions. We know that the Hamiltonian is a Hermitian operator, its eigenvalues have to be real. The same thing for the momentum. Momentum operator has eigenvalue K1 plus K2. Therefore, K1 and K2 have to be complex conjugate of each other, or at least they have to have cancelling imaginary parts. Then with the if they're complex conjugates of each other, then you see immediately that the energy is also real. So that's good. So if I consider, for example, a K1 which has a complex, an imaginary part, then I can look at my wave function here. And here you see we haven't even specified the boundary conditions here. I haven't, we're just writing the Schrödinger equation on the line. We haven't specified how the thing goes on the thing. We can put it on a circle. We can put it, on a kind of circle with crosses and whatnot, but then we have to be careful. We can put it on the whole interval if we want to. Let's consider the coordinates to go from minus infinity to plus infinity. Then, if I have complex, or if I have an imaginary part to some of the momenta, I end up in trouble, right? So imagine that K1 has, or imagine that we take the limit x1 going to minus infinity on this wave function. Then immediately, from the first term, we see that K1 can only have an imaginary part which is negative. Because if it's positive, the wave function is going to blow up to infinity as I take x1 to minus infinity. And the second term tells us that the same is true for K2. Now if we take x2 going to plus infinity, it's the contrary, then we show that the imaginary parts that the wave function blows up if the imaginary parts of the k's are larger than 0. Okay? So if we require that the wave function has proper limits at plus or minus infinity, we are forced to take real k here. Okay? However, of course, this argument does not hold if we put the system on a circle. Okay? Because then we could have a state where essentially the wave function weight accumulates on one end, and then we can empty this. Okay? So, but there are more. There's much more to be said about that. In the end, the answer depends on the form of interactions that you have. If your interactions are repulsive, then all solutions to the beta equations are for real momenta, real K1, K2. If your C is attractive, then essentially the particles act as a kind of potential well with respect to each other, and then essentially one of them can bind another. Okay? But that takes, C less than 0. So, but, I might make some comments about that later, but if you're interested in that, just read my papers with Pasquale from a few years ago. You'll remember this. Okay, so we can both see. So at first, we will suppose now that the k's are real numbers, because that's the case for the repulsive interactions. Okay, so let me just, before giving you a break, let me just write some final forms here. So this ratio of these amplitudes here takes the form of a complex number over its conjugate. Therefore, we can write it as a phase. Okay? And the convention I'll follow is that I will just write this S2 over S1 as minus e to the I phi of K1 minus K2. Okay, where this phi here, so phi of K, it's an antisymmetric function. So it's just 1 over I log of C plus IK divided by C minus IK. And you can just write this as twice the arctan of K over C. Okay, so I will write this phase here everywhere. So just remember that it is this function here. Okay? So just one word, we've extracted this minus sign here. So essentially when you take two particles through each other, you pick up this minus sign, but then with this phase here. So put the interaction to infinity here. If C is infinity, then this phase here is 0 for all finite momenta. Okay? So that means that when the particles cross each other, they pick up a -1. Okay? So this is like fermions. So when you have infinitely repulsive bosons, they will have signatures of being fermions. Okay? In fact, these signatures of being fermions, they exist for any non-zero C. Okay? And that's reflected in the fact that this minus sign here is conveniently popped out. Okay? It's one way of doing of writing the equations here. Okay, so let me just finish before the break by giving you so our form of the wave function up to this point. So we have psi2 of x1, x2, k1, k2 in d2. So we will write it as e to the I k1 x1 plus I k2 x2 minus I over 2 phi of k1 minus k2. Okay, minus e to the I k2 x1 plus I k1 x2 plus I over 2 phi of k1 minus k2. Okay, so here I have just chosen an overall phase. Okay, we haven't bothered with normalization of the wave function here, but this is already the solution of the Schrödinger equation, including the interaction term, on the line. Okay, so we will start with that after the break and kind of glorify it through many particles. Okay, are there more questions about? All right, so let's start again in 10 minutes.